So it's now my pleasure to introduce Dr. Josie Rawes. Josie is an associate lecturer in our department here in York at the Department of Physics, specializing in radio astronomy and high energy astrophysics. So this evening, she'll be talking about the fundamental concepts of radio astronomy, exploring how we can build telescopes the size of the Earth, and she'll present some current areas of research from fast radio bursts to extragalactic jets and quasars. So over to you, Josie.
Thanks very much, Kieran. Good evening, everyone, and thanks very much to the organisers for the invitation to talk to you all this evening about radio astronomy, and congratulations again to all of those who have received awards. I'm Josie Rawes, and as Kieran said, I'm an associate lecturer here in the Department of Physics. So my research is very much in the field of radio astronomy, but I still remember the first time it kind of clicked in my mind that there are parts of the universe that are not only invisible to us because they're so far away, but because they're emitting light in regions of the electromagnetic spectrum that our eyes can't detect. So the image you can see on the screen is a Hubble telescope image of the elliptical galaxy Hercules A. So that's at the center of this image. Now, this galaxy is about 2 billion light years away, and it's an optical image, which means that the light is emitted at wavelengths that our eyes can detect. So you're seeing all the light from the stars, the billions of stars within this galaxy. And if this galaxy were a lot closer to us, we would be able to see it with our own eyes. Now, this galaxy is about 1,000 times more massive than our own Milky Way. But it kind of looks quite ordinary, so similar to other galaxies we would detect by Hubble, so similar to lots of the other galaxies in this image. Now, this galaxy is far from ordinary, however, because if we look at it at radio wavelengths, we see something completely different. So the purple image you can now see shows massive radio jets, and these are extending millions of light years out into the universe. So the jets completely dwarf the visible galaxy from which they're coming out of. And these jets are really high energy plasma beams, so subatomic particles and magnetic fields that are shooting out at nearly the speed of light from the center of the black hole at the center of the galaxy. Now, we'll come back to radio jets a bit later on then, but as you can see, there are these massive structures in our universe that are completely invisible to the eye, but play a hugely important role in the evolution of our galaxies and can reveal information like about very elusive objects such as black holes. Now, I'm sure most of you have covered the electromagnetic spectrum before, but we'll have a quick recap just so that we can put into context where radio waves sit in comparison to other forms of light. So I'm going to attempt here to draw a line that just shows spectrum of light at different wavelengths. So these wavelengths are getting closer and closer together in theory. So please excuse my drawing. This is my electromagnetic spectrum, and it goes from long wavelength light to very short wavelength light. So radio waves sit here at the long wavelength light side. And over on the other side, we have things like gamma rays. So this is the gamma wavelength. And somewhere around the middle is our optical wavelength. So radio waves, they can be anything from kilometers, so maybe 10 to the power of 4 meters, to millimeters, so 10 to the power of -3 meters in wavelength. Our optical wavelength, that would be somewhere in the range of about 10 to the power of -7 meters. And our gamma wavelength, we're looking at about 10 to the power of -12 meters. Now, we can also use our spectrum to describe the energy carried by these waves. So at the long wavelength side, this corresponds to low energy waves. And at the other end, we have our high energy waves. So radio waves are describing the lower energy wave on the spectrum. And in fact, that the energy of a radio wave from a distant radio source is so low that we have to make up our own new unit in order to describe the intensity of a radio signal. And we call that unit the Jansky. So I'm introducing you to a new unit where 1 Jansky, which we denote by JY, is about 10 to the power of minus 26 of the usual units for intensity we would use. So divide most things by 10 to the power of minus 26, and we're talking about the kind of wavelength, the kind of intensities of these radio signals. So for example, the radio signal that your mobile phone will receive, that measures at about 10 to the power of 10 Janskys. The radio signal that the sun is giving off is about 10 to the power of 4 Janskys. However, the radio signal detected for one of these distant radio sources with these jets is about 1 Jansky. So we need to be able to build a telescope that's capable of detecting very, very weak signals and also signals from things really, really far away. So another important concept to consider when doing radio astronomy then is the concept of resolution. So that's how well your telescope needs to be able to see an object. So for those of you that are keen photographers, you may be familiar with the concept of resolution. It essentially describes the ability to distinguish 2 small objects as separate objects rather than one. So I'll show you what I mean by that here. So here is my homemade video, and we've got a cat sticky note stuck to a wall, and it's got a black line through the center, okay? Now I'm gonna press play. And you can see that as I start to zoom in, or in my case, walk towards the wall, you can see that it may not actually be a solid black line. In fact, it's actually many small dots close together. Now, the point at which we would say this image is resolved is the point at which you can see each individual dot. Another video for comparison. This time I'm just walking away. So to start with, this time you know there are individual dots, and as I walk backwards, it appears to look more and more like a solid black line. So the point at which you can then no longer tell that they're individual dots, and then it goes into this more blurry line, that's again the point at which your image would say to be just resolved. Okay, so there's a mathematical formula then that relates the resolution of an object to the diameter of a telescope and the wavelength of the light that you're looking at. So this formula is given by, so the resolution is equal to a constant, which is called 1.22, that's just the value, times the wavelength of the light. So here I'm going to call that lambda, the Greek letter lambda, to show the wavelength, divided by the diameter of the telescope dish that you're looking at. So as I already mentioned, the wavelength for kind of an optical telescope, so similar to a telescope you could buy for a shop, for example. And so the wavelength for optical light I mentioned was somewhere around 10 to the power of minus 7 meters. And the wavelength for a radio light was at its kind of smallest about 1 millimeter, so 10 to the power of minus 3 meters. So we can see already here that if you want to look at the same object at with a radio telescope as you do with an optical telescope, you're going to have a diameter that's about 10,000 times bigger in order to see the same thing. So in order for the resolution of your telescope to be the same, to see an object in both optical and radio, you need to build a telescope with a diameter that's about 10,000 times bigger. So let's take a look then at some of our optical telescopes and get an idea for what an optical telescope looks like. So this first one on the top left, this is the Gran Telescopio Canarias in La Palma in the Canary Islands. This is one of the world's largest optical telescopes. So it has a reflecting dish of about 10.4 meters, so 10-meter large dish. Our second image here on the right, this is the Hubble Space Telescope. So you may recognize this. This is up in orbit around the Earth. And the resolution on the Hubble Space Telescope is about 0.1 arc seconds. So about 1,000 times better than the human eye. So to put that in context, so from its position in orbit around the Earth, Hubble would be able to tell if two people were standing on a beach with beach balls, Hubble would be able to tell, like we did with the dots on the cat post-it note, Hubble would be able to tell if they were one object or two separate objects, and that's from its orbit in space. So Hubble has excellent resolution. And the third image shows an introductory level optical telescope that you could buy easily. So these telescopes don't have huge lenses, but using one of these means you could see planets and other objects within our solar system really easily. So you don't need a huge diameter for an optical telescope in order to see quite a lot more detail about things in our own solar system. So I've mentioned that a radio telescope, however, needs to have a much, much larger diameter. So let's see what a radio telescope looks like then. So the largest fully steerable radio telescope is this one on the left. This is the Green Bank telescope in West Virginia in America. So it has a diameter of 100 meters across. And by fully steerable, I mean that you can move this in different directions across the sky. So that's the largest steerable dish that we have so far, so 100 meters. So that's not quite the 10,000 times larger that we need in the optical. This second image on the top right, this is the Arecibo radio telescope. And keen James Bond fans might recognize this from the GoldenEye film. I think there's a scene with Pierce Brosnan running down the dish. So this isn't a steerable dish. This can only look directly upwards, essentially, and it always looks at the same part of the sky. And although the Earth is rotating, so you do see different parts, it's then not possible to see, for example, the southern hemisphere if you're observing from the northern hemisphere. Now, Arecibo, unfortunately, has met an untimely death recently, and we can see that in this video here. So here we can see this is the footage recorded of the complete collapse of this telescope. So it was quite an old telescope, so a lot of its functions no longer worked anymore, but this was kind of the final straw in that it completely collapsed in on itself. So I think we can also see a drone angle of this, of some of the wires completely giving up. So here's the moment that the supports give way, and this ultimately results in a lot of things falling inwards into the dish. So Arecibo is no longer recording anything useful in the sky. So that's Arecibo, and then on the bottom right of this image, this is the VLA radio array. So I've shown you from Arecibo that you can't steer this, and Arecibo is about 300 meters wide, so that's about as big as we can build. So you're then limited, really, if you can't build bigger than 100 meters for a single dish that you can steer, then what can we do? And the solution to this comes in the form of building a telescope array. So these are individual radio telescopes that can be linked together to form one giant dish. So the VLA in the image I've shown you, this is 27 individual dishes, each with a diameter of 25 meters. So you link these together and you combine the signals, and this forms one huge telescope. Okay, so now that we know how to detect radio waves, let's have a think about why, for example, you'd want to look at radio emission rather than optical. So say you want to look at, for example, the North Star in the sky, okay? There's a few restraints on when you would be able to observe the North Star. Firstly, you would have to wait until it was dark. So that's not to say that the North Star isn't always there and that it only comes around after the sun sets. It's just that the light from the sun overpowers all the light coming from the stars during the day. Now, this is less of a problem with a radio telescope, as the sun isn't a huge emitter of radio waves in comparison to the universe. Therefore, you can use a radio telescope during the day. Now, the other limiting factor you might have, if you wait till nighttime to look at the North Star, is that it could be cloudy. So if there's clouds in the sky, you're not going to be able to see anything. Now, radio waves are completely unaffected by clouds and dust, and therefore it doesn't matter what the weather is, which is great if you're building a radio telescope in the UK. So you might be aware that many optical telescopes, like the one in La Palma that I showed you, they have to be built on the top of mountains where there's very little cloud cover, but you could build your radio telescope anywhere. And when we move actually further along the electromagnetic spectrum, so if you wanted an X-ray telescope or a gamma ray telescope, well, these waves can't even penetrate the surface of the Earth's atmosphere. So if you want to build one of these telescopes, you have to put your telescope in space. Now, radio telescopes can be built on Earth because all the waves can penetrate through our atmosphere, and it makes it much easier to build a telescope if it's on Earth and to fix it if something goes wrong. So where do these radio waves that we want to detect come from, and how are they produced then? So in order to answer this, I think we need to take a look at this object. So have a think about what object you think this is, and I'll give you a clue. It's a planet in our solar system. Okay, so I will tell you, in fact, that this, maybe you'll guess it from this image, this is in fact Jupiter. So this image on the left shows the radio emission coming from the planet Jupiter. So you'll notice that there's strong emission at either sides of the kind of main body of the planet. And this is at the area that we would call the pole of the planet. And this is because the poles of Jupiter are surrounded by a very important physical phenomena, and that's a magnetic field. So when you have a really strong magnetic field, you get electrons, and these electrons spiral along the field lines and can give off photons. Okay, so give off light. So you've got your electrons, and when they interact with a strong magnetic field, they give off light. And it just so happens that this light that's given off is in the radio part of the electromagnetic spectrum. So therefore, we detect radio waves. And therefore, if you can map the radio emission of an object, then you can infer the presence of a strong magnetic field. So if we return to our Hubble image then, this is a Hubble image showing hundreds of galaxies. So each bright point you can see on this image here, this is a galaxy, and each of those galaxies is containing billions of stars. So lucky for us, at the center of each of these galaxies is a mysterious object that has a very strong magnetic field, and that object is a black hole. So what we could do, we could zoom in to look at just one of these galaxies. So for example, the one in the center. So if we zoomed right into this galaxy and looked at it, in the optical, what we would see is all the light coming from all the stars within that galaxy. And if we could zoom in really close, what we might see is an accretion disk of material. So kind of like a disk of stuff swirling around the center, and what we would assume at the center is a black hole. So the gravitational pull of our black hole is so strong that stars and things moving around are being pulled apart, and you just get a swirl of material close to the center of that black hole. Now, as this material gets closer and closer to the black hole, conservation of momentum throws some of the particles back away from the black hole. So imagine you're swinging a ball on a piece of string, okay? And you're swinging it faster and faster around in a circle. If you let go, that ball's going to fly off sideways, okay? The ball wants to be thrown outwards. And that's similar to some of this stuff moving around in the disk, going really fast. So as a consequence, you can get some streams of particles. So these are mainly electrons and protons that have been thrown out from close to the black hole. So I'm not saying they've been in the black hole and come back out. I'm saying they're thrown out from the disk that's circulating really close to the center. Now, if you combine that with the really strong magnetic fields that black holes have, then we've got the ideal scenario for this synchrotron radiation, where the particles are spiraling in this magnetic field and you get radiation at radio wavelengths. So I'll show you a video that shows this then. So what we can see in this video then, we've got our elliptical galaxy, okay, and the reddy orange color, that's showing us all the light from dust and stars as it falls towards the black hole. And the greeny blue emission, that's our radio light from the electrons being thrown outwards and giving off photons at radio wavelengths. We can also see the magnetic field lines around which these particles are spiraling. And these jets extend well beyond the visible part of the galaxy into the space between other galaxies. And so therefore they play a role in how a galaxy evolves, because it's throwing huge amounts of material out into this space between other galaxies. And it's not clear yet whether these jets are emitted continuously. So is the jet always there, or does the jet only occur when something large falls in and gets thrown out of our accretion disk? So looking at the structure of these jets then is really important to working out properties of the black hole, such as how strong is the magnetic field at the center and what is the mass of the magnetic field at the center. And these things are really hard to work out for black holes because we can't see them. So we have to use things like jets, which infer their presence in order to work out some properties. So I'll just play that one last time. So we can see that our black hole is kind of eating something, and these as things fall in towards it, and some particles are thrown out, and so we get our really large jets. Now, jets are not always as straight as they appear in this video. So if they were left completely undisturbed by the environment, then they would eject just straight outwards and continue on beyond the galaxy. But however, space is full of other stuff, so lots of dust and gas, and this can interact with our jets to produce some really spectacular shapes. So for example, this is 3C31. So they don't have very exciting names. They're just named after the survey that detected them. And so we call this one 3C31. So right at the center of that image, that's where the black hole is. And you can see two jets coming out in both directions, and they're bright to start with, and then they're getting fainter as they carry on emitting. And they're both becoming quite wiggly in this image. So this happens when the speed of those jets drops, and then they're vulnerable to other gas like X-ray gas. So they can interact with other forms of electromagnetic radiation, so not just in the radio, but in the X-ray or the optical as well, and that's causing them to start to wiggle. My next example, this is 3C75. So this is an interesting example. Here we have two supermassive black holes. So those are the really bright spots, kind of near the lower half of the image. And the kind of swept back appearance of these jets is produced by the rapid motion of the galaxies. So they're moving through other gas within a big cluster of galaxies. So their motion is kind of similar to how if you're on a roller coaster or something, your hair might get swept back because you're moving so fast through it. So these galaxies are moving so fast through their cluster that their tails and their jets are being swept back by the environment. And you can see at the top of this image, actually, the two jets are interacting with each other. So we've got 4 jets in this picture, essentially, 2 from each of those black holes. And towards the top of the picture, the 2 jets are interfering with each other. And that can happen if you've got 2 black holes really close to each other. And the final example I'm going to show you today is what I like to call the donut galaxy, for obvious reasons. This is a galaxy that I looked at for many years and was lucky enough to visit the VLA in New Mexico, so the telescope array that I showed you earlier, when they were pointing the telescope at this object for new observations. So the core of the black hole is at the center, so the really bright white bit in the center. And then we've got the main jet sweeping back, so towards the top of the image. And on the opposite side of the jet, however, instead of a nice straight jet, what we've got is one that appears to be bent a full 360 degrees round in a circle. Now, this is really rare, and there are only a few kind of possible explanations that could explain this motion. The first is that what we could be looking at is kind of a helical motion of the jet, and we're just looking at it face on. So if you imagine like a slinky that stretches like this, and it's in a kind of helix, that we're just looking straight down the barrel of the slinky. So it looks like a circle, but it could in fact be a helix. And the other option is that there's some kind of turbulent hot gas in the environment that's pushing it round. But so far, we don't actually have any evidence for this hot gas at any other wavelengths. So work on the donut galaxy is still ongoing. So in order to get a better idea then of what's going on with these jets and how they're anchored to their black hole, we need to build bigger and better telescopes. Now, I showed you the VLA array, the 27 dishes linked together in the New Mexico desert, but we can go beyond this. What we can do is we can link telescopes between different countries and even between different continents. So this, if you linked it between lots of continents around the world, this would be equivalent to building a single dish with the diameter of the Earth. So then we're really approaching that 10,000 times size of the optical, and even going beyond the capabilities of an optical telescope. So we're creating a telescope essentially with the diameter of the Earth. Now, building the telescopes themselves is easy. You don't need to build the individual dishes that large, and we can link together existing dishes. So I don't know if anyone's ever been over to Jodrell Bank in Manchester, for example. So their Lovell telescope is part of a network that connects to other dishes around the world. So building them isn't the actual problem. One of the biggest problems we have at the moment is how to store the data that all these telescopes combined are generating. So for example, if you link 20 telescopes together across the globe, this requires storage of an exabyte a day. So the exa part of that is 10 to the power of 18. So I'm sure you're aware of megabytes and gigabytes. An exabyte is 1 billion gigabytes, and that's per day. So say you've got a smartphone, okay, and if your smartphone has storage of 64 gigabytes, okay, just a normal phone, you would need 16 million phones a day in order to store all that data. Another example, if you're on your phone, okay, if you've got your phone and you're browsing all day, so downloading stuff all day, that's maybe 20 megabytes an hour that you're using. You would have to be browsing for 6 million years to use up the same amount of data as an exabyte. So working out how to process the data in real time is really important so that you don't have to store all of it. You can work out which bits are useful, which observations are good, and get rid of all the other stuff without having to find a way to store an exabyte of data a day. However, when it works and when you can store the data, it works really well. So some of you may have seen this image of a black hole. So this was published in early 2019. And this uses that kind of cross-globe technique that we've looked at to produce a really high resolution image of what's going on super close to the edge of a black hole. So this uses this Event Horizon telescope, and you can see the network of telescopes that that's using, and that's covering pretty much every continent, including one on Antarctica. So that's pretty much covering as much as the globe as possible. And we can then get a really high resolution image. And so more and more arrays like this are being built. And so hopefully over the next decade or so, we'll start to see more and more of these images. So this was of a black hole in our neighboring galaxy, but hopefully we can start to look at more and more further away ones and see if there's any similarities or differences. So another goal then that we could start to look at if we can build all these arrays are fast radio bursts. So these are radio pulses that we're detecting from space, and they last from somewhere around a millisecond. Okay, so you know, we're talking about 1,000 a second. So that's how fast one of these bursts is. And this is caused by some kind of high energy astrophysical process that we don't even understand. And the average single burst in a millisecond releases as much energy as the sun does in 3 days. Okay, so that's in 1 millisecond, we've got the same amount as energy as the sun in 3 days. And therefore they must be emitted by an object that's really, really energetic at its source. So really high powered object. The first burst was detected in, I think, about 2007. And more are being detected now because we're now starting to look for them. So it's not that they're only just that it's something new that's being emitted. It's just that that was the first one we detected, and therefore we're kind of targeting telescopes in order to detect them. So I think in June this year, we detected over 500 of them. So our current best guess of what could be producing these fast radio bursts is something we've called a magnetar. Okay, so it sounds a bit like something from science fiction, but it's essentially a type of neutron star with extremely powerful magnetic field. And it's thought that the decay of this magnetic field is what powers the emission of the really high energy radiation. So like other neutron stars, so a neutron star is formed when a really massive star collapses. So like other neutron stars, magnetars are thought to be about 20 kilometers in diameter. So that's actually really small if you think about it. So 20 kilometers, less than something like the length of the English Channel. Okay, so you could fit a magnetar in the English Channel. However, the mass of this object that you're putting in the English Channel is about 1.5 to 10 times the mass of the sun. So you're putting an incredibly dense object in the English Channel. And actually, the density of a magnetar is so high, so you've got so much mass in such a small volume, that if you had a teaspoon of it, if you were able to take a teaspoon of your magnetar, it would weigh over 1 million tons. So that's what we suspect may be causing these fast radio bursts. And the active life of a magnetar is actually quite short, so only about 10,000 years. And there's thought to be about 30 million inactive magnetars in the Milky Way. So being able to detect these fast radio bursts would therefore point to where they are. So I've said they're really small, so it's really hard to know where they are. But if you can detect these bursts, you could pinpoint where they are, and we could then draw a map of their distribution around the Milky Way and other galaxies. So hopefully that's given you a flavor of some of the exciting physics and astrophysics that can come from looking at the universe at a different wavelength. One of the biggest arrays that's currently being built, the Square Kilometre Array, or the SKA, and that's being built between South Africa and Australia. That should be operational mid-2020s, so maybe 2025. And so science from that will start trickling in the late decade of the 2020s. So perfect time for any of you students thinking about going to university in the next few years and pursuing research in physics and astrophysics. So you could be having an active role in analysing results from one of these new up-and-coming surveys and investigating some of the invisible light in our universe. So thank you very much for listening. And yeah, I'm happy to take any questions.
Great, thank you very much, Josie. So in terms of questions, I think there are a few questions that have been coming through the Q&A, and if anyone wants to add to those, you're welcome to do so. So turning to them, the first one was, you had that really nice video of the radio waves coming from a black hole, the animation that you showed. Is there a possibility of creating, real observations, real videos of the actual processes, rather than cartoon, as it were?
I mean, some of these things are so far away. We're looking at things that are the ones that we call near are about 500 million light years away. So currently, no, although it's not known, there is evidence that our own Milky Way has at some point emitted light like this, but objects are just too far away in order to do something like that. So we can only make animations or get still kind of images, because they're emitting for millions of years. So we can get a kind of snapshot of what it looked like this decade, and we could even get one next decade, but that's not going to look much different considering the timescales over which they emit. Okay, sure. And the next question, I think one of your slides probably answered this, which was, how far apart does each telescope have to be for a global array? There's no kind of set distance, but the better coverage you have, the better, right? So the more telescopes you have, the better, and the further you want them to be further apart, because then they're looking at a different part of the sky. So you want to cover all of the sky essentially with the combined telescopes, and the further apart they are, the bigger the distance being covered by them all. So ideally you would have some in each continent, and that are representing each part of the sky. Okay. Another question, how is a magnetar different from a pulsar? Okay, so it's just by the strength of their magnetic field. So if it's got a super strong magnetic field, we call it a magnetar. And the way to distinguish that is by looking at how fast it rotates. So pulsars rotate really, really fast, like hundreds of times a second, but magnetars actually rotate slower. So if it shows this slower rotation, it's thought to be because it's got such a high magnetic field. So you can say that it's a magnetar rather than a pulsar. Okay, and with optical telescopes, it's well known that there's a lot of controversy about light pollution in the sky in terms of things like low orbit kind of satellites. What about with radio astronomy? Is there a problem with suddenly all the background radio transmissions that are occurring in the world? Yeah, so I mean, radio frequencies are taken up a lot by communications. So satellite communications, even mobile phone signals. Some telescopes that I've been to, they can tell when as you approach that your mobile phone has not been turned off. So there's a huge amount of interfering signals. There are a few protected bands for astronomy that you can't transmit signals in, and that protects a bit of astronomy. But there are big problems with communications, and you can extract the signal, but as I said, the signal that you're receiving on a mobile phone is thousands of times stronger than the signal you're receiving from these things from space. So it's quite easy for your signal to be completely dwarfed by interference from things on Earth and even things in buildings nearby and electronics and things like that. So it is quite difficult. You have to know how to extract the signal from the data.
Okay, so there's some more questions coming in as we speak. Next one is, as a radio astronomer, how often do you get asked about SETI? How correct is the physics in the film Contact? Could radio astronomy detect an alien signal? Well, you know,
I think if it's going to detect a signal, it could well be at radio wavelengths. You know, given the long wavelength of a radio signal and the fact that it can penetrate the Earth's atmosphere. So a gamma ray signal might not reach us because it would be stopped by the atmosphere, but a radio signal could. So yeah, I mean, it's still an active area of research for that reason. But you know, what is the chance that the signal, you know, we've only been doing radio astronomy for 50, 60 years with good instruments. So what are the chances that the signal sent was within that 50, 60 year period? Just have to hope that they keep sending the signals.
So another question, if radio waves are low energy, how can a magnetar or accretion disk associated with it release so much energy? Are you not observing the higher energy photons and inferring they're there? Or is it just some redshifted process?
Yeah, good question. So they are super high energy. They do emit also super high energy, but there is a distribution. So you do get some at radio wavelengths as well. Okay.
And given the time, and I promise that we will be as quick as we can, I'm going to finish with what I think is a really good question, which is, what does an astrophysicist do on a day-to-day basis?
Oh, it's very exciting. So today, for example, the University of York has a new radio dish, a new 3-meter radio dish. So today I was on Astro Campus moving it around the sky and seeing what I could see. I'd love to say every day was the same, and a lot of telescopes can now be operated remotely, so you don't have to go and you don't have to be there. But some of these telescopes are at such amazing places that sometimes you want to make the case that you do need to be there. I'd like to be there in person to see it point at my specific object in Hawaii, for example. But yeah, now that you can operate these things remotely, I'd say more time is spent just trying to, for me personally, extract the good data from the bad data.
Yeah. So just finish with a couple of, again, technical questions. Do we know why magnetars have very strong magnetic field?
Not really, no. I mean, they're such a new area of investigation. We don't know why some stars that collapse to neutron stars have a higher magnetic field than others. It could be to do with the original mass of the star itself. But yeah, we don't know. Good question.
Why are the jets emitted in a straight line? When they're, you know, you saw those images where you occasionally had things moving around, but it's quite striking how straight line, you know, they were really quite discrete straight lines.
Yeah, so it's kind of from the conservation of momentum and the fact that we think that it's quite a symmetrical magnetic field from these objects, so they're just spiraling along essentially. And yeah, unless stopped or deflected, they will just go straight.
Okay. Well, I think we should leave it there in terms of the Q&A session. Again, if we were all in a room together, we could all, you know, clap, cheer, hoop, and kind of, you know, congratulate Josie on what's been a really, really nice talk. So thank you, Josie. And finally, thank you to all the teachers and parents who've come along, supporting the students, and also throughout the whole period that we've been through over the last year or so, being able to support them in very difficult circumstances and ensuring that their talent comes through and they get the recognition they deserve. So it has been wonderful to see the array of different talents, and I really hope, whether it be in physics or elsewhere, I hope that you've been inspired by physics, and that you take it on with you in your career, whatever you end up doing. But I do also hope a lot of you will go on to do university physics and beyond. So thanks very much, everyone.